So a couple things from 8.5. Yes, you could find the next row by always adding, whoops, if you could add right, 4 plus 6, 10? No, there we go. 5, 1. You can always find the next row by adding the previous row, and one of the things that you did in 5.1 was realize that these are combinations. Now you can memorize that this is 0, choose 0, 1, choose 1, 1, choose 0, 2, choose 0, and figure out which row. What I find really easy for the memorization is just take a 4. 4 is obviously 4, choose 1. That's really easy math to do. 5 is 5, choose 1. If I know that that 4 is 4, choose 1, that would tell me this is 4, choose 0. After 4, choose 1 is 4, choose 2. 4, choose 3, and the last one is 4, choose 4. Now it's important to know that these numbers in Pascal's triangle are related to combinations, because we're going to have a formula that connects that today when we look at doing the algebra for expanding. Now, some of these you already have done. For example, x plus y squared, you could FOIL that out, multiply it out, x plus y times x plus y, and you would get x squared plus 2xy plus y squared. And I'm adding ones there, but you would never write those ones. But I'm going to add those ones there because we're going to look at a pattern that occurs. For example, if you did x plus y to the 1, well, to the 1 would just leave you with x plus y. And I'm going to add ones in front of there. And anything to the 0 is 1. Okay? Now, if you did x plus y cubed, it actually would be, you would have to do this. Algebraically, this is all you could do right now is x plus y times x plus y times x plus y. And you know that 2 of them, we already figured that out, so this would equal x squared plus 2xy plus y squared, and that still needs to be multiplied by x plus y. And then you would have to do all the arrows and distribute that again. And the result you would get looks like this. X cubed plus 3x squared y plus 3xy squared plus y cubed. And if I wanted to, I could put ones in front of there. And what our brains should be doing right now is saying, ooh, I saw some of you realize one pattern already. Could you write the next row without actually multiplying out x plus y times x plus y times x plus y times x plus y? So see if you can write out the next row on your own. I'll put up the answer in like 30 seconds, and then you check to see if you discovered all of the patterns. And if you don't get some patterns right, then it's going to be like, okay, what patterns was I missing? And feel free to look up whenever you're ready. how did you do? Are you noticing Pascal's triangle is showing up? Kind of made that obvious because I made it in blue. Sorry about that. You notice the pattern in the exponents. That when the exponent is 4, you start with an x to the 4. And then each time the x's go down by 1 until there's none left. And you start with 0 y's, and each time the y's go up by 1 until you get to y to the 4. And in any given one that you look at, so for example, if I look at this one right here, there's 3 x's and 1 y. There will always be 4 things in total when the exponent is 4. When the exponent was 3, there was always 3 things when you added up all the variables in total. And we're going to look at why this happens. Okay? Why do these numbers, which are related to combinations, now happen in algebra? So if I took x plus y and I multiplied it by x plus y, by x plus y, by x plus y, you probably from your polynomials unit realize that we often just multiply these first ones together, and those first ones together gave us an x to the 4. That probably makes sense for your first ones. Okay? And in our polynomials unit, we were really only worried about the first ones and the last ones. In our polynomials unit, if you look here, you see that if you multiplied all of your last ones together, you would get y to the 4. Okay? But those aren't the only arrows that happen. Like, we usually just do the arrows for foiling, right? First, outside, inside, and last, and do those 4 arrows. But what happens when you're doing multiple multiplication? Everything in the first term could get multiplied by one thing in the second, then one thing in the third, then one thing in the fourth. And there would be a ton of arrows if we tried to draw everything. But when looking at this one that I circled in green, the green one has 3 x's and 1 y. Does it make sense that the 1 y could have been this y with the other 3 x's? It could have been this y with the other 3 x's. It could have been, oh, I'm getting fancy colors here, this y with the other 3 x's. And finally, it could have been that y. There happen to be 4 y's, and we need to choose which one we're going to use. When you multiply them together, does the order matter in the end? No, you just move things around. But you have 4 y's, and you choose one of them, and that's why there's going to be 4 x cubed y cubes. If I chose 2 y's, as in this one, there'd be 4 choose 2. Now, I decided to talk about y's so that it matches up perfectly with what we wrote at the beginning, with starting with 4 choose 0, because you see in the very first one, there's no y's. 4 choose 0. But you could also think about it as choosing x's, because 4 choose 4 is the same as 4 choose 0. And 4 choose 3 x's is the same as 4 choose 1 y. That part doesn't matter. And what happens as a result is we can find these blue coefficients because of that. And then, that's how many times you're going to get an x cubed y if you did all of the arrows. And if you combine like terms, that's why we're going to get 4 of them. Question?
Since you add the first 2 to get the one thing, right? How did you get the coefficients or the x's and the y's?
How did I get the blue numbers?
Not the blue numbers, the powers.
On the left-hand side here?
No, here.
Here?
Yeah, like the powers, like x to the power of 3. How'd you get the powers?
So, if, we'll look at the x to the power 4 one. If I was multiplying 4 things together,
Yeah.
and I look at my first terms, which are all x's, Can you see that you'd multiply x times x times x times x? And you would get x to the 4 if there was 4 of them. If there was only 3 of them, you would only get x cubed when you multiplied the first.
No, that's not what I mean.
Okay.
The numbers in the middle. The
The-
4, the 6, and the 4.
The 4, the 6, and the 4.
Yes, they're
Yep.
x and y values. How did you get the coefficients? The powers.
So x to the 4, we'll start with x to the 4. And then the pattern is it's going down by 1 for x's. What's 1 less than x to the 4? x3. Then x2, then x, then no x's. And we start with 0 y's, and we go up by 1, up by another 1, up by, until we get to y to the 4. Because the first one, which we show with the green hops here, multiplying your first ones would give you x to the 4. The last ones is the purple ones. That's the very last one's going to be a y to the 4. In between, like in this green box, this is saying if I want 3 x's and 1 y, I have to decide which y, the yellow, the orange, the purple dotted, or the red, which one is going to be the y. And then I would multiply, for example, this red one would be like, I multiplied this x, then the y. And that would give me 1, 2, 3 x's, x cubed, and 1 y. But there's 4 different options for that. And it appears 4 times. So the thing that we realize is that when we do a binomial expansion, binomial because there's 2 terms inside the brackets, and an expansion because we have an exponent, which means we have to do repeated multiplication. When we do a binomial expansion, the coefficients of the terms we can get from Pascal's triangle because they're related to combinations. So when we go to example 1, a couple of other patterns that we could have noticed that are going to help us. Actually going to go back to that previous slide just temporarily here. One of the things I want you to notice, and I find it's easiest to think about this one because this is the one you know the best. You've squared so many things already by the time you get to grade 12. If you square something, does it make sense that here you would have 3 terms? When you multiply it out, you got an x squared, you got the 2xy, and you got a y squared. You end up with 3 terms. When the exponent is 3, we have 4 terms. When the exponent is 4, we have 5 terms. So when we look at our first example here, I notice that the exponent is 4. You will always have 1 more than the exponent as the number of terms. This is helpful because if I look at my Pascal's triangle, which row will I have to go up to? I have to go up to this one that has 5 numbers. So if my exponent is 4, it's going to tell me, hey, there's going to be 5 terms. In Pascal's triangle is going to tell us the coefficients. We have to go up to the row that has 5. And now I can start by saying, I know that 3b minus 1 to the 4 is going to equal, and I'm going to space this out, 1, 4, 6, 4, 1. So I can space out my coefficients already. What was the pattern with the terms? The very first one, can you see that the very first one would have 3b times 3b times 3b times 3b, so that'll be 3b to the 4. And it would have none of the minus 1s. Plus, the second one, well, now that'll have 3b cubed and 1 of the minus 1s. Plus, the third one will have 2 of the 3b squared and 2 of the minus 1s. Then 1 of the 3b's and 3 of the minus 1s. And finally, 4 of the minus 1s. So if there's a subtract sign, we just put that negative with that second term and multiply it out. What we've done right now is, in the instructions, we did the expanding part. And this is a lot faster than actually doing, I mean, I could give this to my grade 10 students and say, yeah, just multiply 3b minus 1 times 3b minus 1. Do 2 things at a time, keep getting bigger and bigger until you get your final answer. But that's time consuming, and this is a bit of a shortcut by noticing the connection to combinations and to Pascal's triangle. Now we can simplify. Okay, so I'll do all my exponents first. The 1 doesn't matter, but 3 to the 4, that'll be 81 b to the 4 plus 4, I'll do the exponent first, this will be 27b cubed, still times a negative 1, plus 6. This will be 9b squared, and negative 1 squared will be positive 1, plus, this will be negative 1 cubed, negative 1, plus, and negative 1 to the 4th will be plus 1. So I just did my exponents first. If you want to do more mental math and skip a step, that's okay, as long as you don't make mistakes. And now I can do the rest of this. I don't have anything more, but here, negative 4 times 27 is going to be negative 108b cubed. 6 times 9 is 54b squared. 4 times 3 times negative 1 minus 12b plus 1. And there we have our final answer, simplified and combined everything together. So we use our Pascal's triangle to get the numbers in front. Then we use the pattern. And again, if you think back to, like if I actually wrote out 3b minus 1, 3b minus 1, 3b minus 1, 3b minus 1, and I think about those first ones, right? And this is what you used in chapter 1 in polynomials. You often had to think about your first ones to find out if it was an x to the 5 equation or an x to the 4 equation. Does it make sense that you would have 3b to the 4 in that first one? And in your last one, here's your last ones. You're going to get a minus 1 to the 4. But now we're seeing what happens in the middle. And the idea in the middle is that the second term, you're going to take 3 of the first ones and 1 of the last numbers, but you have 4 choose 1 ways of picking that last number. And then the second one, you're going to use 2 of the first ones and 2 of the last ones when you multiply it out. And you have 4 choose 2 ways of choosing that last one, or the first one. That is the idea that we're looking at. Okay, questions for practice on this one are 3 and 4.